Today we're here to talk about explicit dynamic analysis, specifically structural explicit dynamics in Ansys Workbench. And I titled this or subtitled this webinar At a Glance, because really I just want to scratch the surface of the capabilities of these tools within Ansys Workbench. Just knowing that you can really, devote yourself to learning and properly applying these tools, but I also wanted to show how accessible they are. So we're really going to just sort of scratch the surface in terms of understanding the capabilities and the applications for both LS-DYNA and Workbench and the Explicit Dynamics system component. So really quickly, a bit of background on myself. My name is Hunter Norgard. As I said, I am the MBU Mechanical Business Unit Team Manager at RAM Simulation. RAM Simulation, if you're not super familiar with us, we are the 2019 Ansys Americas Partner of the Year, and that is after being around for less than one full year at the start of 2019. So as an Ansys channel partner, so we really have hit the ground running and really claimed our spot as a channel partner to look out for in our space. My personal background is that I have a degree in physics. I come from the material handling and automation world before joining RAM Simulation, specifically for feed mill automation. And this is my 8th year with RAND and with the entire RAND worldwide team. And really excited to be here to talk to you guys about this subject matter. I want to really start by saying that I am far from being the greatest authority on explicit dynamics, even just on the RAND simulation team. Really, I'm an enthusiastic beginner, and what I wanted to show was that while explicit dynamics might seem intimidating as a discipline up front, it really can be more accessible than a lot of people think. And wanted to clarify as well, for those of you who might be joining, this will not be a technical deep dive. This won't be a really strictly academic level discussion, but it'll sort of straddle the line between the sort of information you can get, with a sales briefing on explicit tools versus a really deep technical investigation into their capabilities. It's going to kind of straddle the line between them. And I am specifically talking about explicit dynamics in Workbench, not AutoDyne as a standalone tool, and not LS-DYNA as it couples with LS Prep Post or any other third-party tool. All right, so our agenda for today, I'll go over really quickly, give you a really brief background. For those of you who are new to explicit dynamics and the explicit method, I wanted to, at a very high level, explain, what's going on, under the hood and compare it to the implicit method so that you understand why explicit dynamics are a unique approach to solving problems. Talk about when it's appropriate to use explicit dynamics over implicit. Outline the two options for explicit dynamics in Workbench. One of them is actually called explicit dynamics as a tool, which can be kind of complicated. So I'll probably just refer to explicit dynamics, the discipline or the approach, as explicit, and explicit dynamics as the tool, to be clear about which one I'm talking about. The other being Workbench LS-DYNA. Talk about some concepts that are directly related to explicit dynamics that you'll need to be aware of when you start diving into that world, just because there are some things that really are critical to understanding to being successful explicit that I want you to be at least aware of before you start investigating the capabilities of that software. And then I want to go through some of the fun stuff, which is specific applications for Workbench explicit simulation. Give you some actual applications so you can start understanding, how this might make sense for you. And I set up all these demonstrations myself. I want to make sure that the workflows made sense to me so that, I could speak to, just what sort of, level of effort you can expect when you go through each type of simulation. And then finally, I want to give you guys, just because there can be a lot of, I guess, incredulity around, okay, sure, you're showing me a really pretty demo, but what about a real world case? What about like a true application? I want to give you a couple of real world case studies that we've performed as consulting projects using the Workbench Explicit tools. So you can see what these things look like in action. So a really brief background, and I mean this when I say very brief on explicit dynamics, because I'm only going to touch on the theoretical foundations of this approach. Starts with the equation of motion for a transient structural problem. If anybody on the call has ever taken on any sort of transient structural analysis, you probably know that what you're really trying to do is solve this motion equation for each node essentially in your model. And that's going to be directly related to the displacement, velocity, and acceleration of each node, right? Now, each of those terms is also going to be coupled with a matrix. So the stiffness matrix for displacement, damping matrix for velocity, and the inertial properties or mass matrix for acceleration, right? And essentially what we need to know is where is each node, where is it going, how fast is it getting there? And then all the stresses and strains and et cetera kind of get derived from the state of the system after it's been deformed, right? That's true of FEA in general, right? Now, what complicates solving this equation is the fact that deflection, velocity, acceleration are all interrelated as terms. So acceleration is the derivative of velocity, velocity is derivative of displacement, et cetera, right? So you can't just find a direct solution because those terms are related to each other. Now, I want to focus on kind of the more complex part of that, which is the expression related to stiffness. You might recognize this as Hooke's law. So if we're looking at a really simple one-dimensional system, and I'm keeping it simple, particularly because the math gets much more complicated the more degrees of freedom we add into a system, right? But if we just take a very simple 1D system comprised of 3 nodes connected with 2 springs, we can express this system in terms of a matrix. And then that matrix can be then expressed in terms of a number of linear equations. Now, this is really integral to the implicit approach, and the reason why this is done is because that matrix can be simplified. You can go through a process called factorization, which is some linear algebra magic essentially that allows you to reduce the complexity of that matrix, and you've got a simpler set of linear equations to solve for. And that's all really fundamental to this implicit approach that we're talking about. Now, another component that's really integral to this implicit approach is the concept of convergence at different load steps or time steps. So whenever you're running a nonlinear analysis, what you're really doing is you're running a test force on your system. And if this graph looks a little messy, I'll try to break it down into steps. So essentially what's happening is you're going to apply a test force to your system. Then your matrices that describe your system are going to be reformulated using what are called Newmark parameters. And you're going to end up with a new set of displacements, velocities, accelerations than where you started from with your system, and a new equilibrium force for those nodes. And you can compare that resultant force with the test force that you apply. For the first iteration, basically that's never going to line up with your test force, right? So you have to go through this process several more times. So you're going to reformulate the matrices, get a new resultant force, you probably get a little bit closer, and on and on and on until you reach convergence, until your resultant force matches with your test force. That's what's called a Newton-Raphson iteration, right? And that's how you can achieve convergence between your steps. Now, where this contrasts with the explicit method is that using explicit dynamics, there's no matrix formulation. Sometimes I think I've heard it referred to as a right-hand only approach, meaning that only the linear equations are considered in this case. That has some huge ramifications because a lot of your system memory, a lot of the CPU time is spent assembling and decomposing that stiffness matrix. Secondly, there is no need for convergence, which is huge. If anyone here has tried running a nonlinear analysis where the conditions of the system change really rapidly, let's say your material goes from an elastic state to a plastic state, you'll notice that the time steps start converging more and more slowly as time goes on, as that system becomes less and less linear. And finally, the reason that the explicit method is so huge is it involves a direct solution to that motion equation. Now, I shouldn't say that you can just solve that equation without any sort of approximation. You have to use what's called it's based on the Runcuta method for solving ordinary differential equations, which, I break into a cold sweat every time I think about my differential equations class in college, but it provides a way to solve these equations using a number of terms. The simplest is a single term. I think it's referred to as the forward Euler approach. And one of the more complex approaches is a 6-term. I think that's the Dormand-Prince approach. And so you can find a way to, essentially approximate where your system's going to be using any number of those terms, which will increase or decrease the accuracy of the solve. Now, the catch, and this is a very accurate way to go about solving problems. The catch is that this only works as a transient solution, which can be kind of a big deal when you want to do anything that involves slowly applied loads or really long-running analyses. So the question, becomes implicit or explicit. What's the right analysis approach for me? You might look at this and go, oh, great, I don't need to do this, or my program doesn't need to do this complicated matrix math, this complicated linear algebra. It doesn't need to go through conversion steps, so it solves much faster. Why wouldn't I use explicit dynamics for everything? And the reason why is because each analysis method has its strengths and its limitations. So the strengths of the explicit approach is, again, there's no matrix formulation, there's no need for convergence. It also generally uses less memory because so much less has to be stored as a process of decomposing that stiffness matrix, for instance. Another huge advantage is that contact can be simpler. Contact is sometimes a really messy problem in implicit solutions. You have to define all of your contacts. You have to, look into your crystal ball and figure out what components come in contact with each other. And you can set up what are called body interactions in explicit dynamics that will essentially track any components coming in and out of contact for you automatically. It's excellent for simulating anything that's short duration and highly dynamic, anything where the state of the model changes very rapidly. So components coming in and out of contact with each other. The nonlinear material properties coming into play, things that change the conditions of that system really, really quickly that normally would cause really difficult convergence in an implicit analysis. And as a result, you have a greater number of what are called equations of state that you can work with for your materials. So simulating the way that fluids or explosive materials will behave now becomes possible. It also lets you simulate extreme nonlinearity, complex material behavior in terms of like extremely high strain. So that allows you to simulate buckling behavior very easily. It allows you to simulate forming operations quite easily. You get greater flexibility with different types of element domains, not just your typical Lagrange domain, but also Euler domains, what are called smooth particle hydrodynamics, and even what's called the arbitrary Lagrange Eulerian domain, which we'll talk about really briefly. And then time stepping is generally done automatically by the solver, which is nice. There's no user input. Implicit strengths, in general, there are a greater number of methods that you can use. So I'm thinking specifically about things like linear dynamics. If you want to understand how a system will respond to a shock or vibration load, there are analysis methods that you can employ that really take advantage of the matrix math. So they're a little bit stronger on that front than the explicit method. Yeah, so there are some benefits to that matrix assembly. Any analysis that involves a long runtime and longer time steps, usually implicit, there's a point at which the implicit approach makes a lot more sense. I put this in here and I, kind of gone back and forth. Parallelizing a solution, splitting the solution up between multiple nodes in a solve cluster is supposed to be, or is supposedly a bit more efficient with implicit, although I think LS-DYNA actually parallelizes quite well. There's two-way FSI using implicit methods, so coupling with a CFD study, for instance, in Workbench is possible, and then that can be a two-way coupling, so the deformed shape can go back into the CFD study. Versatility with boundary conditions and joints that you just don't get with explicit studies in implicit, and there are lots and lots of options for structural elements that you don't get with the explicit tools. So some of the limitations of explicit dynamics, you're kind of forced to use really short time steps, and I'll get into the reasons why shortly. The users that are taking advantage of the explicit method have to keep an eye on energy levels in the simulation and energy error. This is a transient only approach. There is something called quasi-statics, which we'll touch on, but it's not true static analysis. Not all material models material models that are available in implicit studies are available in explicit. So for instance, I think certain hyperelastic models that are available through engineering data you just can't use. It doesn't have two-way coupling with CFD systems. There are a couple fewer structural element options with explicit dynamics depending on the tool you're using. And then not all your boundary conditions are going to be available. Certain ones just don't work with explicit tools that you get with implicit structural analysis. Of course, the limitations for implicit analysis, the struggling to converge between steps, right? Especially with complex material properties, changing system conditions, contacts, et cetera, et cetera. Not great for highly dynamic simulations. A lot of memory can be consumed. That can sometimes be a real showstopper within large implicit systems or large solutions on large systems using the implicit approach, I should say. Time step sizing has to be manual a lot of times. And then there are definitely limitations on the sort of material types in terms of equations of state, which we'll get into. So sorry, I know that was one of my wordier slides, but we're going to get through the death by PowerPoint and get into some of the interesting stuff here shortly. So as far as what the best applications for explicit dynamics are, starts with drop testing. That's really kind of straddles the line between where implicit methods work and explicit methods. I will say that I vastly prefer using explicit methods for drop testing because it can involve some really dynamic responses that, again, you start getting, some convergence issues with an implicit solver. Any sort of high and hypervelocity impact, buckling and post-buckling behavior, any sort of blast, detonation, deflagration, anything that blows up, really. Forming in a situation where you get extreme strain, especially things like, like drawing, forming, crimping, that sort of thing. And then any highly complex materials can be simulated really, really well in explicit dynamics. And that all goes back to the fact that convergence isn't an issue. So let's talk about the two options for using explicit dynamics in Workbench. The first is what used to be called explicit STR. I think that's the name of the solver still, but the system component is just called explicit dynamics in Workbench. That's the name of both the tool and also the analysis method. I think it's been around since around 2009. That's when I first was able to dig up any information about explicit dynamics. It is a system component in Workbench. As I said, it uses the Ansys mechanical interface for pre and post processing. The solver is based on the Autodyne solver. So if anyone's familiar with that solver, it is one of the best solvers out there for any sort of blast simulation. And one of the great things about explicit dynamics is that it comes along with Ansys Mechanical Enterprise and all the benefits of that particular package. So contrast that with Workbench LS-DYNA, and a few of the key facts about that tool. It is really, LS-DYNA is the name of the solver itself. It's not an all-in-one solution. It's been around since the late 70s. It was acquired. LS-DYNA is created by a company called LSTC, and they were acquired by Ansys last year. There has been a version of LS-DYNA available through Workbench since 2006. It's actually been available with mechanical APDL since the 90s, I believe. But as of mid 2000s, you could get it as a system component in Workbench. Again, works through mechanical as the pre and post processor, and it becomes available to you when you purchase an Ansys LS-DYNA license. There are two LS-DYNA options that you can get through Ansys. One is the traditional LS-DYNA license, the other is the Ansys LS-DYNA license. And it's the Ansys LS-DYNA license that gives you access to LS-DYNA inside Workbench. All right, so I want to talk really quickly about the strengths and limitations of each of these tools. So strengths for Explicit Dynamics, it comes with Enterprise, all the benefits of that package, all the higher level material models, the additional solver capabilities, all of that is included when you're looking to leverage Explicit Dynamics. It's a little bit more fully integrated with mechanical, uses most of the same boundary conditions, the same objects, that sort of thing. It also has a few more useful presets in terms of analysis type. So I'm talking about drop test versus high velocity, low velocity, quasi-static, etc. It uses Ansys HPC licenses, which is huge. So if you're already using HPC licenses for other types of solutions, CFD, mechanical or otherwise, you can use those with Explicit Dynamics. It does enable blast simulation, kind of on a basic level inside of Workbench. It has great performance with really dynamic, really short duration simulations, although that does start to drop off a little bit the longer running the simulation is. And it has a greater number of element options just in general. So for instance, you can use pentahedral elements, whereas you can't use those with LS-DYNA. Now some of the limitations, and there are a few more than what I listed here, it's not as good for lower speed simulations. So when you're talking about quasi-statics or things like buckling simulation, it's just not quite as strong of a tool as compared to other explicit options. It's also not capable of handling any user input for the solver file, so no command snippets. Right? It's a closed file format for the solver file. Now, compared to Workbench LS-DYNA, really its strengths are that LS-DYNA is the industry leader for a lot of different applications. I mean, specifically crash testing, but it is a true general purpose tool, and it's really the gold standard for explicit dynamics on the market. It's an incredibly useful, versatile tool. Very fast simulations, especially for lower speed applications. As I said, highly versatile. It also installs, if you get Ansys LS-DYNA, it comes with LS Prep Post, which is a pre and post processor that really allows you to utilize that solver to its full capability. Whereas there's some limitations to using it inside of Workbench, LS Prep Post lets you have all the power of that solver at your fingertips. And it also, allows you to, when you purchase Ansys LS-DYNA, use that solver with other third-party tools if you have a different prep post that you want to use. Excuse me. It's really excellent for simulating complex material behavior, large strain simulations. It has some UI components that are really specific to LS-DYNA simulation that you get essentially different contextual tabs in the ribbon with different commands when you run this tool as compared to, for instance, Explicit Dynamics, which really uses the same commands, same boundary conditions as any structural simulation in Workbench. It has some better options for implicit pre-stressing. So if you want to preload your model using what's called a dynamic relaxation, you can. It has an open format solver file. So you can use command snippets to, for instance, define material properties. And it allows for second order elements, not just linear elements. Some of the limitations that you should be aware of, it does require the purchase. If you want to use more than one core, you have to purchase LS-DYNA HPC licenses. So there is an additional cost if you want to leverage multiple cores for that simulation. And a few of the mechanical interface components don't work the same. So for instance, joint loads inside of LS-DYNA. For the most part, what I found is that if there's something I'm trying to do in terms of applied boundary conditions, there's a workaround. Some of the concepts, once you start, approaching this explicit method and trying to leverage it for your own purposes, there are going to be some concepts that you really need to be aware of in order to do it properly. This is by no means comprehensive. So if this is the direction you want to go with your simulation efforts, definitely dig into the training materials. But I wanted to at least prime you for some of the things that you're going to learn about. Starting with the CFL time step. Now, the CFL time step is really a measure of how quickly information can travel across an element. So for a structural element, that's going to be directly related to the speed of sound within that element. It's also going to be related to the dimensions of that element. So the shorter an element, the shorter the time step. And what difference that makes to you is that, and I should state this another way to say that, if you were to restate that expression for the time step and pull out all the parts of it that are related to the element dimensions, you're left with an expression for the square root of the mass over the stiffness of that element. So whereas the time step will scale linearly with an element length specifically, it has a nonlinear relationship with material mass and the material stiffness, which means that in general, your element size is going to be the driving force or the more significant force behind how long your time steps have to be. And why that's significant is because the time step size in explicit simulations is always much, much smaller than in implicit studies. So if you watch the solver progression of an explicit study, you'll see that the cycle count, or if you're paying attention to how many iterations the solver is going through, is going to be huge compared to an implicit study, easily in the millions for a longer running simulation. In most cases, the total duration of the simulation needs to be fairly short. There are some guidelines, generally speaking, as far as like how long a simulation should be for any type of particular simulation. We'll get into some of the minutiae of that in a minute. Generally speaking, we're talking about millisecond or tens of millisecond runtime or shorter. And then each time step itself, each cycle utilizes that CFL time step plus a safety factor that you should apply. And when we talk about the order of magnitude of those steps, we're oftentimes talking about microseconds or even nanoseconds in time step length. So really, you need to keep an eye on the size of your elements very, very carefully, because the length of the solve time for your problem is going to be directly related to the shortest element length on the smallest element in your model. You can have a really coarsely meshed model, you have one small element in there, and that's going to drive up your solve time precipitously. Now, some of the positive aspects of simulating using explicit dynamics is you get to leverage element erosion, or sometimes called element failure, element deletion, what have you. Essentially, when your elements hit some sort of limit criteria, whether it be limit strain or element quality, it hits a minimum Jacobian, for instance, you can have that element just simply delete, and that can simulate failure in materials really, really well. Now, it's been pointed out to me before that implicit methods also allow you to do this at some level, where you can set the depth of an element based on certain criteria. It's really baked into the explicit software in a way that makes it much easier to leverage, though, when you're running these sort of simulations. So if you want to simulate breakage or any sort of like gross failure, it can be really, really useful. And again, this ties back to the fact that there's no need for convergence with the explicit dynamics approach. The state of the system in one time step can be completely different than the state of the system in the next time step. So having things like elements delete out and the general stiffness characteristics of the entire system change rapidly, not a problem in Explicit at all. Whereas that would really throw an implicit solver through a loop, for a loop in a lot of cases. Another concept to watch out for, this is one of the less fun ones, hourglassing. This is a tendency for elements, especially, well, particularly, I should say, hexahedral and quad elements in your simulation to deform in a way that actually requires zero energy. It's a real peculiarity in terms of behavior inside of explicit tools. So there are different mitigation techniques for adding some artificial stiffness, for instance, to those elements to prevent them from doing that. Something to at least watch out for, because that'll be one of the things that you need to keep an eye on is if you add some artificial stiffness to those elements, you know, what sort of energy are you seeing going into keeping those in the proper shape? So I was talking before about how the explicit approach is really only for transient simulations. There is a way that you can leverage it for longer runtime simulations through an approach called quasi-statics. And it's essentially a way that you can kind of emulate static loading. But what it really requires is that in your simulation, you don't expect to see any dynamic effects as any sort of vibration within your structure, and you won't have to worry about any sort of inertial effects, meaning you're not using a gravity load and you don't have any components that are like impacting each other. This approach will generally increase your solve time because, again, explicit dynamics requires the use of very, very small time steps. There's some ways that you can play around with that. One of those ways is by really damping down your system to like eliminating sort of dynamic effects that do emerge. And another way is through mass scaling. So mass scaling is a way that you can artificially increase your time step size by adding mass or material density to the materials in your model. Basically make everything heavier. And that goes back to that expression that I used where I pulled out all the stuff related to the element proportions and I just put in a variable called A. You can forget about that. Essentially, you look at the term M at the top of that equation, and you can see that, okay, the more massive I make my material, as in the more material density I give it, the longer my time step size can be. And you can inflate that artificially, and that will allow your time steps to be longer and your simulations for long running simulations to go more smoothly. Now, depending on who you ask, this isn't a great approach necessarily for quasi-statics because you can get really massive energy errors that way. You know, if you think about the equation for kinetic energy, it's something like 1/2 mv squared. So if you double the mass of your materials, you're doubling the kinetic energy. And because energy is the way that explicit dynamics really track error in your simulation, you can introduce a lot of error that way. So this isn't necessarily the most, I guess, sound method for simulating quasi-statics. Also, there can be no inertial effects if you're using mass scaling. So again, no gravity loads unless you know exactly how much mass scaling is going to be applied. And you certainly don't want things to hit each other because if there's any sort of impact, that impact is going to be significantly harder as a result of that artificial mass inflation. And then this can be done either automatically through the solver, or you can manually just add more density to your material. Another one of the fun ones in terms of things that you can now do with explicit dynamics, you'll have access to more equations of state. So you can think of equations of state as, you know, if I push on my material, how is it going to behave? You know, what's the sort of response going to look like for that material? The simplest is going to be just Hooke's law again, spring force law for elastic materials. But there are equations of state for things like, like liquid bodies and understanding the shock pressure and resulting particle pressures within that body. There is an ideal gas equation of state using this adiabatic pressure expression. And then there is the JWL expression, equation of state for detonation, which describes material behavior before, during, and after that detonation. And that allows you to simulate really cool stuff like blast, anything that blows up. In addition to those new equations of state, you're also going to have access to a few more types of domain. So the typical FEA domain, as we all know it, is going to be the Lagrange domain. That's where the elements themselves deform. But there's also the Euler domain, which is a little bit more typical of CFD analysis, where material flows through the elements. The elements themselves don't change shape. There is kind of a hybrid of those called arbitrary Lagrange Euler. Now I should add that ALE, as it's called, is not really something that's typically done through Workbench. I think it's possible to do through LS-DYNA, not something that I've done myself. But that's essentially where you've got a solid or a structure embedded within a fluid field in most cases. And then the last is going to be smooth particle hydrodynamics, which is a mesh-free type of idealization. It is awesome for simulating extreme distortion, but more specifically for non-ductile materials. And that smooth particle hydrodynamics, or SPH approach, is actually a newly unlocked feature within Workbench that you can leverage. All right, so now that we're through all the tedious stuff, I want to show you some applications for how you can actually leverage this software for your own purposes. And it really starts again with drop testing. Drop test simulation is very, very easy to set up in both Explicit Dynamics and in LS-DYNA and Workbench. The drop test wizard is an ACT extension that you can install that, it comes installed, that you can enable, that will allow you to set up your drop test simulations very, very quickly. And it will automatically set initial conditions, create an impact plane, mesh your model if it's not meshed already, configure your analysis settings specifically for that type of study. Now, because drop test simulations can sometimes be a little bit more long running, I did a really quick comparison study between both an Explicit Dynamics setup and an LS-DYNA setup for the same model, which is a scope being dropped from a height of 4 feet. Might have been 6 feet actually. The results are ever so slightly different on those two models. There's slightly more plastic deformation in the Explicit Dynamics setup. And that's largely because I had to use a different mesh on both. They're similar, but slight differences in mesh between those two models. But the big difference is with default settings, because you can always tweak settings in both tools in terms of solver behavior. But with default settings from that drop test, Explicit Dynamics had a bit longer runtime than LS-DYNA, which kind of shows that LS-DYNA has some benefits in terms of these longer running, slower simulations. Another great application, anything that involves high velocity impact. So ballistics is a great example of that. This is a great demonstration as well of how different element failure approaches can change your results, especially at the local level. So I used default element erosion settings or element failure settings for both LS-DYNA and Explicit Dynamics on this ballistics check. And you can really see, as far as global behavior of the two plates that the round impacts, the global behavior is the same between them, but you do get slightly different local effects. And that's largely due to the fact that there was some compressive strain failure criteria that was being used in the Explicit Dynamics setup that wasn't being used in the LS-DYNA setup. And that really, again, can change, some of the local level effects within your simulation, those little nuances in terms of how elements are going to be removed. Again, one of the more, how to say this, cool, one of the more exotic analysis methods that you can take advantage of, specifically in Explicit Dynamics, is blast simulation. You'll have access to a library of explosive materials, explosive equations of state, and that also gives you access to what are called virtual Euler domains, so you can simulate a fluid field and actually set off or detonate that explosive body within that field and have that pressure wave then interact with your solid structure. So I did this for kind of a mocked up submarine hull, and I wanted to study then what happens to that hull when a depth charge is set off next to it. And as you can see, it doesn't hold up the best. But the idea being that this is something that you couldn't even dream of doing using traditional implicit methods. Another great application is forming, and LS-DYNA really shines in this area. Anything that involves material forming, whether it's bending, drawing, stamping, again, crimping, just because in explicit dynamics, I've said it once, I'll say it again, the fact that you don't need to worry about convergence means that anything that involves extreme amounts of strain really don't trip the solver up, where it would be very difficult for an implicit solver to simulate that. Now, I will say that forming simulations are probably best done in LS prep post, and a lot of that has to do with the fact that there are specific solver commands what are called keywords that can be leveraged for forming simulations, and I think that interface just lends itself better to really simulating the conditions of, let's say, measuring spring back in your formed part a little bit better than doing it through Workbench. That's not to say that can't be done through Workbench, or that Workbench doesn't have some great potential when it comes to forming simulations. One of my favorite areas of leveraging explicit dynamics has got to be buckling. Buckling is another one of those situations where, because you don't have to worry about convergence, the explicit solver can just handle those simulations so much more easily than an implicit solver. And the reason why is because buckling by its nature involves instability within the model. And anytime there's instability, anytime something in the model changes, so the same amount of force will result in not just one deformed shape, but it will continue deforming, because at that point the structure is no longer able to support that load at all. It'll keep deforming, keep deforming, keep deforming. A static approach to that sort of nonlinear buckling, especially when it involves things like material plasticity, is just not possible. Now, there's the arc length method using an implicit solver, which has some applicability here. What I found is that, explicit solvers just do this, so much better. And it's great for understanding post-buckling behavior. I used LS-DYNA for this particular demonstration, and this solved very, very quickly. Part of the reason why is because I wanted to create a very large model that I knew would have large elements that would solve quickly, but we're talking about, a few minute runtime for something like this. I'm not a particularly prodigious machine. Now, one of the more interesting areas of simulation, a capability that's been added in the last couple of years to both LS-DYNA and explicit dynamics, is the incorporation of smooth particle hydrodynamics. These particles are really, really great for simulating, anything non-ductile that's going to experience some extreme deformation. This is actually from a demonstration that Ansys has put together for a bird strike on an airfoil. And my team and I kind of thought it would be interesting to see what would happen if that bird were considerably larger and potentially angrier when it struck the airfoil. And really, the results are pretty interesting to look at, pretty cool looking. But this has applicability in a lot of different areas. I've also seen an SPH idealization used to represent an open surface fluid body, and a vessel or a ship on top of that fluid body, and how it responds to rolling waves or an explosive charge being set off underneath it. It's really a powerful way of representing both fluids and, in some cases, solids as well, with low structural stiffness and not much ductility. So those are all ways that you can leverage the software. I wanted to really quickly touch on a couple of applications that my team and I were actually involved with leveraging explicit dynamics in the real world. One case involved a customer of ours that was developing a protective cage to put around a pump wellhead. So this is for the oil and gas industry, and this involves a lot of active drilling around these sites where oil is being pumped out of the ground simultaneously. So a lot of heavy equipment being carried through the air above these very delicate wellhead structures. And they have to design a cage that will essentially protect, some of the more delicate equipment that's in use. And what they couldn't, really tell us was, or tell themselves for that matter, was, how does this cage hold up if we drop something heavy on it? So more specifically, are we expecting gross failure in this cage structure that we're building if, for instance, a large section of drill pipe were dropped onto it from a height of 50 feet? And the simulation that we performed actually showed them that while there is definitely penetration of that drill pipe into that frame structure, it is thick enough to arrest the momentum of that drill pipe, and we don't see gross failure in the form of, that wellhead being impacted. So some of the significant factors in this simulation, again, how we approached element erosion. One thing that I talked about with the team afterwards was, we might have been a little, conservative in terms of how we predicted element erosion. I think we might have over-predicted failure, which is fine because we wanted to make sure that this wouldn't fail. We didn't need to necessarily define the exact degree of failure, but more just, will this hold up under expected loads? So defining the failure criteria properly, it was really important to understanding exactly how much penetration would occur and making sure that our material models emulated material stiffness properly. So we used, I think in this case, a Johnson-Cook model for material stiffness rather than something like a bilinear material model, which might be more typical in an implicit analysis. And then the other case study that I wanted to talk about really quickly involves another customer that's designing essentially a dirigible. It's a large airship that needs to be able to withstand certain wind loads or gusts without exhibiting certain deformations within the outer envelope or the outer enclosure of that ship. And what we were able to do is leverage explicit dynamics to simulate how that material would behave. And what we found was that, under the weight of the keel that is supported by that envelope and due to just, typical sagging behavior, that does create some rippling or some ruffling of the material that also changes the aerodynamic properties of that ship as well. And really that would have been something that would have been difficult to do in any sort of implicit study, is emulating that material behavior that realistically. So having gone over all that, really, I hope this was informative to everybody understanding what some of those differences between the implicit and explicit methods are, seeing how this software can be leveraged. Again, I am certainly not going to give you the most technical explanation of the tools, but there is a ton of information out there for you on both tools. There, in the Ansys Learning Hub, there are now over 20 LS-Dyna classes you can take now, for instance, and there are Workbench classes for both Explicit Dynamics and LS-Dyna that you can take that are incredibly informative and really go into the theoretical foundation of both tools really, really well. If you want to know more about RAND simulation and some of the other work that we've done, you can check us out on LinkedIn. You can go to randsim.com to see our website. And I would also encourage you guys to check out our blog at blogs.rand.com/randsim. And you can see some of the cooler things that we have done.